Hello everyone, and thank you for watching this video. I'd like to talk through some intuition about collisions and as it relates to linear momentum. This is for a Chapter 9 Physics 1 calculus-based class, and I would like to start off with these simulations. So have a look at this website, PhET, which is Physics Education Technology, and we'll click on Physics, and that brings up this site. We'll click on Motion, and then we will, under Motion here, we will then scroll down, and we will click on the one that says, where is it here? The Collision Lab, so right here. Okay, so the Collision Lab is right here, and then it looks like this. And then when you click on it, now you have to allow Flash Player to proceed. You might have to change the settings or permissions on your web browser, but I can guarantee this is a safe simulation. I've never gotten any viruses or anything from it. So what we're going to do is we're going to look at several situations of balls colliding and interacting with one another, and between each slightly different scenario situation, what I'm going to do is I'm going to have you predict what should happen. I'm going to show the simulation, and I'll show various variables that go along with this situation, okay? And we can look at the variables velocity, momentum, center of mass. We can look at a diagram of the momentum. We can look at the kinetic energy, and we can also just show the numerical values the entire time, okay? We can also set the elasticity or the sound. Okay, so what I have here to start is I have a red ball and a green ball, balls 1 and 2, and they're each set to the same mass, namely 1 kilogram. Okay, and what we can do is with this initial velocity of 1 meter per second, notice that there's also going to be a momentum of 1 kilogram meter per second, because 1 kilogram times 1 meter per second, just 1 kilogram meter per second. Okay, so I'm going to predict when these two balls hit and they're elastic. So think of elastic as bouncy balls. What should happen when these balls collide? So hopefully you had a chance to think about it. And let's see. I think what should happen is ball 1 should stop, ball 2 should move with the same velocity that ball 1 was moving. That is, ball 1 should transfer all of its momentum and all of its kinetic energy into ball 2. And that is exactly what we observe. If you show the values, notice that the velocity of ball 2 is now positive 1 meter per second for its velocity. Notice, let's call the positive x direction to the right in this simulation. And furthermore, let's describe this all in terms of one-dimensional collisions, a single axis. So if I bring the balls back and instead I show the momentum vector, okay, and suppose I show the momentum diagram, notice that all the momentum before the situation equals all the same momentum after the situation. Okay, so let me actually reset one more time. Yes, okay, so this is the momentum before. This is the momentum after, and all the momentum just transfers from ball 1 to ball 2. Okay. Notice that all the momentum is the same thing as the total momentum in this case. Okay, this is a pretty straightforward diagram. Hopefully you get the idea. Now, let's try another situation. Let's reset this situation with the same two balls, but now let's make a slight change here. Let's have ball 1 be twice as massive as ball 2. So twice as massive as ball 2. So now ball 1 is 2 kilograms, ball 1 is 1 kilogram. Think about what you think should happen in this situation before you come back. So hopefully what should happen is ball 1 comes in with 2 kilogram meters per second of momentum. Ball 1 has only has no momentum to start, but because ball 1 is much larger than ball 2, ball 1 has a lot of inertia, has a lot of momentum, so ball 2 should move off very fast, and ball 1 should actually keep continuing going. Let's go ahead and see what that looks like. First with velocity, then with momentum. Okay, so let's go ahead and play. Notice this is what we see. Okay, watch it one more time, but this time watch it with, again, ball 1 having 2 kilograms for its mass, and ball 2 having 1 kilogram for its mass. And then let's instead look at the momentum vectors and the momentum diagram. Okay, so let's do this. 3, 2, 1. Notice this is what we observe, and if we show the values, notice that ball 1 came in with a momentum of 2 kilogram meters per second. Notice that that is equal to the total momentum of the system. But after the collision occurred, ball 1 has a smaller amount of momentum than it did at first. Ball 2 has a more momentum than it had at first because it had 0. But now look, the sum of the momentum of each ball added together is the total momentum of the system. That is 1/3 of a meter per second times 2 kilograms gives 2/3 kilogram meters per second. But look at this ball. This ball has 1 kilogram times 4/3 meters per second. And I think that 2/3 plus 4/3 is 6/3, which is 2 kilogram meters per second. Notice that's exactly the same total momentum we had before. Okay? So this is kind of the idea. All right, let us restart again, but now this time, let's change it to be the other way around. Let's let ball 1 be 1 kilogram, and let's let ball 2 be 2 kilograms. Okay, so it's just the other way around. Let's again have ball 1 have an initial velocity of 1 meter per second, and let's have ball 2 be at rest. So I'll stop and give you a second to think. Talk to your dog, talk to your cat, talk to your neighbor, whomever is there, and make a prediction. This is a good way to learn. Okay, welcome back, and hopefully you paused the video and had to think about this. Ball 1 should actually bounce back this time because ball 2 is larger. Now ball 2 will still move forward, but it won't move forward as fast as ball 1 did because it's a larger mass, it has larger inertia, thus larger momentum. So it's going to have larger momentum just in terms of its mass, but let's see how it plays out. So 3, 2, 1, go. Notice what happens. Ball 1 hits ball 2. It was moving at 1 meter per second. Ball 1 rebounds back with negative 1/3 meter per second velocity. Okay, remember the direction's important here. Momentum is a vector. Negative means to the left. Yeah, when it comes to momentum, the momentum is negative 1/3 kilogram meters per second. Okay, that's because it's 1 kilogram times negative 1/3. Look at the velocity of ball 2. It has 2/3 of a meter per second, but it has 2 kilograms. So that should be 4/3 kilogram meters per second. But notice that's because 4/3 positive kilogram meters per second plus negative 1/3 kilogram meters per second is 1 kilogram meter per second. That should be the same momentum we started with. Let's in fact show the momentum diagram and the momentum vectors again. Okay, and let's restart. Notice that the total momentum is all ball 1 to begin. After the collision, the negative momentum of ball 1 and the positive momentum of ball 2 add to the total momentum of the system. Okay, hope this is making some sense. Now let's make one more change. Let's have both balls be 1 kilogram, but now this time, let's give ball 2 a non-zero velocity. So in fact, let's show the values. Let's have ball 2 be moving to the left at negative 0.5 meters per second, negative a half. Now, what do you expect should happen this time? Okay, hopefully you had a chance to pause. They should actually trade their velocities. When the masses are the same, it's a very special case. Remember before, ball 1 would stop when ball 2 would go. And notice that now, since they both have the same mass, they're going to transfer momentum, but they're just going to transfer velocity to each other because they have the same mass. So let's have a look at that. And that is what we see. Okay? Hopefully this looks like billiard balls you've seen before. Billiard balls are going to be the closest collisions I can think of to conservation of momentum in the real world. Okay? But notice that they trade velocities because their masses are the same. Okay? And notice that they're going to change direction from what they originally were. Okay? Let's restart this. Let's show the momentum vectors instead. Okay? And take off the velocity vectors. And let's show the momentum diagram. So notice ball 1 has more momentum than ball 2 at first, but then after the collision, ball 2 has a greater magnitude of momentum than ball 1, but again, their same total momentum adds to the same total momentum we had before. Notice the total momentum of this system is positive to the right because ball 1's moving to the right faster than ball 2's moving to the left initially. But notice ball 2 ends up moving to the right faster than ball 1 was after the collision. Okay, let's try maybe one more scenario. And that is, let's try maybe two more scenarios. Let's try having ball 2 not at rest, but let's try having it move to the right at half a meter per second when ball 1 comes and sort of catches up to it and hits it. Okay, so notice that this time they should trade again because they have the same mass, but I think ball 2 is just going to get a boost. And let's think about what's going to happen to ball 1. Well, it's going to take on maybe the velocity of ball 2. Okay. Let's give that a shot. Okay, so let's go play. That is what we see. That is what we see. Again, it's the trading of velocities. Let's restart this. Let's instead show the momentum diagram and the momentum vectors. Notice the sum of the momentum vectors should be equal to the total momentum, but notice after the collision, they trade each other's momentum with each other, and we have the same total momentum. Now, what about a scenario where, let's say it's something kind of complicated. Let's say it's something like ball 2 is moving to the left at negative a half meter per second, but then ball 2 is also, let's say, twice as massive as ball 1. So let's let ball 2 be 2 kilograms. Notice each of these balls should have the same momentum coming in. So stop and think and predict what should happen. Okay, welcome back. So they are definitely going to bounce off of each other, and they should definitely go in opposite directions. But I'm not sure about the velocities. So let's go ahead and play this. Notice ball 1 came in with 1 meter per second. It goes out with negative 1 meter per second. Ball 2 came in with negative a half meter per second velocity. Ball 2 goes out with positive a half meter per second velocity. That's because the total momentum of the system is actually 0. Why is that? Well, let's take a look at this. Notice that the total momentum of the system is 0 because vectorially these momenta are canceling each other out. When they hit and collide, sure, they change their velocities, but it's just like basically changing their velocity directions. Now then you may ask, what if it's something even more complicated like the following, where, let's say, ball 2 has only half the velocity of, has the same velocity as ball 1, and but it's also twice as massive. So let's show the values. Okay, so let's do this. Okay, so -1/2. Okay, so let's take a look and play. Notice ball 1 shoots out pretty fast compared to ball 2. Why is that? Well, because ball 2 has greater inertia, greater momentum. So even if two objects have the same velocity, magnitude, same speed, but opposite directions, the one with the greater momentum is going to impart more momentum to the other one. Or at least like this will have a larger velocity moving out than this one, I should say. Okay? So that's what we observe. Now, let's see. This is all the conservation of momentum in terms of elastic collisions. Notice that it's elastic because what we did is we set the elasticity to be exactly 100%. What we should also do is we should repeat these same experiments, but we should do them inelastically, where objects stick together. So I will try to do that in the next video. Thank you very much for your attention. I will see you in the next video. Please like the video and give it a thumbs up. Subscribe to the channel, and I will catch you in the next video. Thank you.